Sorry for the hiccup, and thanks a lot for being here. So we have two great presentations from Ian and Christopher. I am going now to talk about a very different topic from the previous two presentations. So we were coming from CQRS, event sourcing, and then the new features in ACA 2.6, which are systems or APIs to program and create parts of an application. And what I want to introduce today is Cloudflow as a way to compose things together, compose streaming applications on Kubernetes, and compose them from different components that are getting data, processing it, and producing it to another component that can be then put together to create an end-to-end application. I am Gerard Maas. I've been part of the Scala community since very early, and also the Spark community since I adopted Spark, and it was like 0.9, I believe. And you can reach me here. I'm also the author of the Spark, the stream processing with Apache Spark, which speaks about the structured streaming and Spark streaming that I will be touching upon today. In terms of some of the programs that we're going to develop and put together. And of course, you know Lightbend, and we all know Scala, and we have been talking about ACA this evening. But we have two new open source projects that are there below. One of them is CloudState. CloudState is implementing serverless functions with state, so many of the serverless experience you have out there with the cloud providers is all about the stateless functions that you will run on Lambda or the equivalent in Google Cloud or Microsoft. And CloudState is adding state to that, and it's adding state precisely by running ACA behind it and keeping that state managed for you. But I'm going to talk about Cloudflow. And before I start with Cloudflow, I like to have an idea of how many of you are using Kubernetes today. All right. So some of you, Kubernetes adoption. Kubernetes is very hot because it's like a very easy way of getting something running from a Docker container. So you have a Docker container somewhere, you write a small file, YAML, hell, and then you can get your first deployment done on Kubernetes. But that's very easy, and it gets you one small container running, and then very fast you want actually to adopt more of the facilities that Kubernetes is offering you. One of those is a deployment where you can say, okay, this is my container, this is my Docker container, so it contains some program inside that I want to scale up. So I can deploy deployment, and I can scale it up or down. And once you see how easy that is, the people next to you see, oh, that's really cool. Well, let's do more of it. And we start deploying more and more things in Kubernetes. And we also want to do some eventing. So we deploy Kafka to it, and we implement an event-based or event-driven system on top of Kubernetes by adding Kafka. But then now we have data and we want analytics. So let's add some more to that. And at some point, it starts becoming, there is no intro here, but at some point it starts becoming complex. And that complexity builds up on you, and when a new person comes into the team, then you have to kind of carry them through that mountain of knowledge that they require in order to become productive. And this causes two main issues in my mind. One of them is when you start having all those components deployed together and they are communicating through a common channel, then you actually don't know what the boundaries are of your system. What is talking to what? How do you deploy this as a single unit that you say, this is my application? And so we want a way of preserving consistency of our applications and our deployment. We can deploy something and not deploy it in one shot. And the second one is about, well, if we have this new person in the team, we don't want them to learn all about Kubernetes and chasing all Kubernetes APIs the whole day to achieve a goal. So we want to reduce complexity. We want to make that easy for everybody. And there is where Cloudflow comes in. Cloudflow is a toolbox. So it's composed of several small components that help you as a developer to create, deploy, and manage streaming applications on Kubernetes. And why streaming? Well, because streaming applications are typically a bit harder. They are composed of elements that need to be connecting properly. And with Cloudflow, we are achieving those contracts that help you ensure that communication is in place. There are two components to Cloudflow, something that you use on your machine to develop, of course, so there are some libraries and a CLI and a kube control plugin, and there is a Kubernetes part to that. On your machine, we offer an API, an abstraction that we'll touch upon in a few slides, where you will write your applications and write your business logic in. Then a blueprint is a way to represent how those small applications are connecting together. Think about connecting inputs with outputs so that things are flowing into a system. Sandbox is, well, luckily I don't have a network connection right now, so we'll be using the sandbox to test and run the things locally before we deploy to a cluster. And we have a number of build extensions that help putting these all together. So it's a bit of glue at the build level to enable you to generate packages and Docker images and all that without having to write a single line of YAML. And finally, there is an extension to kube control so that you can then take those packages and boom, ship them to your Kubernetes cluster of choice. On Kubernetes, we are using the extensibility framework of Kubernetes, the operator pattern, to actually implement something that we call the federated operator approach, where there is a controller operator, this is a Cloudflow operator in this chart, that is going to take care of orchestrating the deployment of your application using or delegating part of that task to other operators deployed in that same Kubernetes cluster. And we are currently supporting Kafka with Streamsy. We are supporting the Spark operator from Google, and we are supporting the Flink operator, as well as our own implementation for an AKA operator that is embedded actually in the Cloudflow operator. And let's motivate the use of this with an example. So we found this at a customer. A customer had built such a system. This is actually a slide of a presentation they created about how they build up their data ingestion system. They have some data produced at the radio towers that is being ingested. And from that ingestion, first you need to do some cleaning on the data. And from that cleaning, we're going to produce some aggregations, and those aggregations need to be stored in different places for different external services. So there is a database there that is going to be, we're going to add data to Cassandra to have a REST API talking to that, and then for a later analysis, we're going to also store the data in HDFS. And what we observe in such a process, in such a system, is that we are dealing with data, so the data has shape, it has a schema attached to that, and we want to make sure that the data entering our system validates against such a schema. So, and also put that the data that is not valid in somewhere. And after that, every single step in that process, every single step that creates a data set that can be reused, but now here we have streams. So if your process creates a stream that can be reused, in that case, for example, we have the aggregation is going to two different places. Well, we call this a streamlet. A streamlet is of course we have the connections, but the streamlet is a concept, of course. It's an abstraction of how streaming works. There is some data coming in and some data being produced, and there is something in the middle that is processing the data to create value from the input to the output. We say, well, every of the inputs and outputs has attached a schema to that, and those schemas are giving particular ways that we can connect things together. So we can validate that if you say this streamlet is producing data and I'm going to connect it to streamlet B, well, then we can validate that that is correct. Whereas if the schema of the output here is not matching the schema of the input of the other, well, we say you cannot connect this. And the build extensions that we're providing will help you out saying, well, this is not valid. I'll protect myself. Okay, and the logic is written using the API that you already know. So if you are adopting Spark structured streaming or Apache Flink or Akka streams, well, we are not reinventing the wheel. We are not providing you here a new API you need to learn. The logic, the business logic written in Streamlets is written in the API of your choice, the ones we support, but it's an inherently extensible system. And we are working on two things. One is making it easier for contributors to add new runtimes, and the second one is to add polyglot support. Because when you are talking data and you're talking streams, the first question we always ask is, we always get is, what about Python? I have some Python machine learning code. I want to run it against the data streaming. Can I do that? Well, we are working on a means to achieve that. And once you have written Streamlets for every one of the components there, well, we want to put those Streamlets together. So we write what we call a blueprint. A blueprint, as the name kind of gives away, is a way to represent how the system looks together, or looks like. And first we say, well, those are the Streamlets that are defined in my system, and those are the instances. You can reuse the Streamlets, like for example, I don't have a reuse there. And then you say, well, those Streamlets are connecting in this way. And then with the build extensions, you can then verify that the blueprint is valid. You can see that all the Streamlets there are able to connect together, and you can run things locally. And run local creates a single VM where all the components are instantiated, and if there are inputs, you get a temporary port for that, or you can execute your end-to-end application without having to first package your Docker, deploy your Docker, upload it to your cloud of choice, and run things, and something fails, and you have to log in into the pod and check for the logs and see that things are working or not. We allow you to shorten that feedback cycle, that inner loop of development that allows us to be very productive. Well, shorten it by running everything locally. And once you know that things are working, then you can build and publish all your application that creates a Docker image that then you can use to recreate the deployment on Kubernetes. So build and publish creates an image. You can publish it to a Docker container. A Docker repository, and then with the Cloudflow extensions for queue control, you can then manage that application. The first thing you want to do is deploy the application, and that deployment will actually produce a deployment descriptor in all terms, where this is actually in terms of Kubernetes is a resource definition. It's a custom resource definition that is being given to the Cloudflow operator, and then the Cloudflow operator will take that definition and command the different subsystems to deploy the parts of the applications that are meant for that system. For example, if we are combining an HTTP ingress and you have a front end to talk HTTP to or JSON, and some Spark to analyze the data, then the Spark part will deploy a Spark container, and the Akka operator will deploy the Akka parts of it. And in the Cloudflow operator also ensures that all the topics that we are talking between the components using Kafka, that all the topics are created and they are managed for the application. And part of the Lightbend offering is adding visibility and operation visibility to that deployment. So if you have a Lightbend subscription, you can attach the console to it and get insights on how your system is running. But let me jump ahead here and give you a small example. So I think it's appropriate being here to give an example about fraud detection. This small example starts from the data science process. So I try to sketch how the data science process looks like here in very rough terms. Of course, if there is a data scientist here, they will say, well, you spend all your time in the data cleaning, all the rest is very easy. But we start from a bulk of transactions, we understand that data, and then from that data we try to create a model, and from that model then we can apply the model to new data that we haven't seen yet, and try to estimate, well, is this a fraud or not a fraud? And this is mostly an offline activity. So we capture data from a period of time, and transaction DB or transaction extract can be for last month or last year. And the model that we want to apply is for the new data that we are seeing. So the relationship of that data science process with that real-time pipeline is this orthogonal chart that I like to represent in this way. So there is data flowing to the system, so there are new transactions coming in, and that work that we did offline and we typically repeat over time to retrain our model, it will actually be feeding that fraud detection streamlet, as we call it, that is part of my pipeline. And I'm going to show how you do this in Cloudflow with some code. Let's first go here and 12. So what I mentioned before is that we start with the data. That's how the data looks like. This is a synthetic data set that has been used to study the problem of financial fraud in mobile transactions, especially in the let's say the new banking models that are being used in Africa, where banks are actually playing a much lesser role, and the transactions of money are going from one mobile to the other. So here they're actually doing a transaction between two mobile users, and there is a certain amount of money that being transferred between the two, with the balance information attached to that. And once we have this, go here. Once we have this, well, we describe that data as we give them a schema. And in this case, we are using Avro to describe that data model. As you see, it corresponds to the fields that we use. So we have a step, we have a type, we have the amount, and the balance, the old balance, the new balance of the data, etc., etc. All right, and I don't know what happened with my network. Okay, so we have data, and it doesn't stop. We have data, and we have the schema of data. What is the next thing that we need to do? We need to see how our data is going to flow to the system. So this is our first. Can you read that back there? Is that big enough? All right. Okay. So this is a streamlet written using Akka streams. It's particularly simple because we offer this. Oh, I shouldn't walk so much. We offer this HTTP server logic functionality out of the box. So you're actually seeing there an oversimplification of what you would do. But if you would be writing Akka strings, then the system would look something like this. Well, the definition of an input, and as I mentioned, our streamlets are defined with inputs and outputs. So we have an input, and the input is of that type transaction. Transaction here is a type that has been derived from the schema definition. So you have the Avro. From the Avro, you compile the types, and now you can use the types to say, okay, this is the input, and this is a typed input for my streamlet. And there is an output for it, which is an enriched transaction. So I depart from a transaction, I create an enriched transaction from it, and what I'm doing is I'm adding some features to that event. And the features are based on the process that the data scientist first went through to create that model. And I can glance really quickly through it. I have not that much time, but this is the typical data science environment. They like to use notebooks, not IntelliJ or any other IDE to work, but this is more of an interactive environment where you can load the data, play with it, massage it a little bit, and also document what things that are going on. And this is fairly long. It's based on a blog post by Databricks. And the important part here is that we do a similar work. We define the type of the data, we load the data, we visualize a little bit what the data looks like. In this case, we created some feed or some data sample to test our job, but we added some features to the data set. So in this case, we added 2 new columns, being the difference of the origin and the difference of the destination, before proceeding to create our model. And our model is created using a Spark ML pipeline that we are going to train using a fairly large data set. So first we create the pipeline, we assemble the pipeline there, we create a decision tree classifier over here, and finally we train that with the data that we first loaded and where we added some of those features, and we save that. Of course, we validate that things are good enough. But at the end, the interesting part for the streaming flow is that we have a model that we can then use into our streaming system to score our data. So we have this model here, and using another streamlet, I am going to load that model. So I am going to first, we are running, of course, on Kubernetes. It means I need to first get that model from somewhere. That model will be coming from a volume mount. So if you have been using Kubernetes, well, data, the local storage is, you cannot load things on your local pod, local storage from the external system. You need to declare volume mounts. We are here loading that volume mount called models, and from that volume mount we are going to load a model file, and that's a model file that has been created by the Spark process. Once we have that, we write Spark code to apply that data to our data set. Okay, so as I mentioned before, this follows the same model. We have an input, and that input is that enriched transaction we had before. It has a schema, of course. We know the schema. This transaction has the additional features added to it. And what we're going to produce is a score transaction. We're going to see, is that transaction valid or not? Is a transaction probably a fraud? And we are going to add some information to that initial event that comes in. We are here using a structured streaming, so we're using a query in Spark structured streaming to take the model that we loaded. So first we load the model here. We say, okay, there is a model on my volume mount. Volume mount will read the model. We recreate a pipeline, a Spark ML model from that. And then on a streaming fashion, we are going to read the data from the stream. That data already has a type, so we don't need to parse it, or we don't need to transform it using any JSON parser or whatever. We know the type of it. It was encoded in Avro already. And then we're going to apply that model using the transform function. Take the data that is coming in. We are going to say, well, is this fraud or is not fraud? And once we have that information, then okay, we have a prediction column there. We're going to call it a fraud prediction. That's what it's going to tell me, was the transaction fraudulent or not. And we're going to keep track also of the model that created that that score. Of course, we want to know afterwards if a transaction is rejected because it was suspicious. We want to know which model said that suspicion was there. And finally, we write this, or we finish this query saying, okay, this is a score transaction. As you see, we are moving from one type to a different type using the schema information that we had at the beginning, and we are preserving that line across our flow. So this streamlet starts from a enrich the transaction and ends up in a scored transaction, whereas the previous one is saying, okay, you have a normal transaction and you want to enrich it. At the end, this is a little bit of, let's say, bookkeeping to write that stream back to the system. What happens here is that it's written back to Kafka to be made available for the next streamlet in that process. Once we have that, and we'll have a look at the blueprint. Once we have the streamlets in place, well, we have the input, we have an enrichment process, we have a scorer and the logger. The logger is just a print line of the result, just to be able to see it. And what we're saying here is that the output of the ingress is connected to the enrichment process. So this is another streamlet. The output of that enrichment here goes to the score, and the output of the score goes into the input of the transaction. And with these two pieces, so we have coded, we have broken down our system into our logical steps that we need to do to create an end-to-end application. We receive the data using HTTP. We enrich the data using the same process that our data scientists used to create the initial model. And then we use the Spark to apply an existing model to the streaming data that is coming in. And once we have all these pieces in place, we can then try to run this. And I can... all right, so the first thing that we can do with our application here, we go to SVT. Of course, we need to compile this to ensure that everything is working properly, but that will be verify blueprint. So verify blueprint, I mentioned it on the slide, but what it's doing is saying the blueprint definition that we have, is it valid or not? So it's going to take the inputs and outputs that we have declared, it's going to take the schema, and it's going to actually verify that the schemas are compatible. Not that they are equal, but they are compatible following the our definition of a schema compatibility. And now we know that this is valid, and we can try to run it. But before we run it, let's do something here. Let's this is something that gets me every time. So if you, how many of you are working with Spark? Some of you. So half of a Spark is type and the other half happens at runtime. All the query analysis and all the creation of your logical plan and physical plan starts at the time that the Spark runs, not at the time that you code your application. So if you make a small mistake like this one, this thing is not going to be caught by your tests, it's not going to be caught by your compiler. I can try to compile this again and it's going to pass, but it will only hit you when you try to execute this. And that typically happens after you uploaded everything on your cloud system and start it up. Run local lets you get those pesky details much faster. So run local starts all streamlets in one JVM. So I'm running 3 Akka streamlets, so those are 3 Akka stream processes and 1 Spark process. They have been all started together in this special sandbox, and the output is available here. We designed it so that the output doesn't scroll here, otherwise you lose important information, like for example, what port can I use to exercise my system. And we can have a look at what kind of information we see there. And boom, we have one of these Spark eruptions of the never-ending exception, and it's going to tell us that somewhere it could not find a column in a table. And right, so cannot resolve fraud prediction given those inputs. Yeah, because we made that silly mistake. So let's fix this and go back to my to my SBT process. All right, I terminate it, I run it again. And I don't know how many of you have been running Spark in production and running on clusters, but it always takes like 10 or 15 minutes before the point that you fix a problem, and then you can run it again. And now you're running it immediately. We can take this, this new temporary file, and this time we should be having something that is running. So this seems to be up. I have something that that generates data somewhere here. So send data, and send data is going to just let me just cut. Okay, it's just taking this sample data set and it's going to stream it into my system, and well, all right. So it looks like I'm sending data, and let's look at my output. And my output looks like it's doing some score. So let's stop the output for a second. And what we see here is that we have a transaction with a given ID, and is given certain score. And of course, we don't have that many fraud cases in the data set, so just from time to time we will find a one there when it's what we caught a bad transaction going through the system. And I'm sure they are there, but somewhere. All right, so we have now our streaming system running end-to-end in our sandbox. And I'm very sorry about this network situation, because the next logical step will be to deploy this onto Kubernetes. I will stop here. I don't think that will work right now. But then I hope you get the gist of it. The idea is of Cloudflow is help you think about your streaming application into logical steps. That's actually how we do it. You go to the whiteboard and you say, here's where we get our data, or good data is going into this system, or bad data is going to a dead letter queue, and from that point on, I want to do A, B, and C, or I want to feed my microservice in a certain way. That mental model is now represented in terms of streamlets, and those connections are represented into the blueprint. Test local helps you accelerate that inner developer circle to be more productive, and also to verify that things are running before you go to your cluster and deploy the whole package in the cluster. We facilitate the deployment and packaging using SBT extensions. And finally, we have the kube control that we cannot show today. Well, we have the kube control extensions to let you manage that application on Kubernetes as well. And at the end, well, if you go with us on our additions from a commercial perspective, then you can also add that UI for operational observability of your application. All right, and I think that is what I wanted to say. What is coming next, as I mentioned, polyglot support. So we are adding support for PySpark and for Python containers. Support for multi-image. Also bring your own Docker image. Right now we generate that image for you. There are many people in their process in the organization. Some other entity generates a Docker container with some valuable systems or models inside there that they want to add to their streaming pipelines, and we are implementing that. Okay, so I hope you get the gist of it. We are an open source project. It's in cloudflow.io, and but we want this to actually preserve consistency of the applications and help you reduce complexity. And before you go,